All right, good afternoon. Welcome everyone to the Georgia Tech Manufacturing Institute's Fall 22 Lunch and Learn lecture series. My name is Dr. Billy D. Brown. I'm a senior research faculty as well as Education Workforce Development Director for GTMI. I'm excited to continue hosting this informative series. This is the second to last lecture for the series. We'll have one more next week. And I should mention next week, the lecture will start 30 minutes earlier, so at 11:30. I encourage you guys to please spread the word as we continue to grow our audience and provide value for the GTMI community. Before I introduce today's speaker, I will first introduce GTMI, provide some brief instructions for the audience. Georgia Tech Manufacturing Institute, or GTMI, is one of 11 Georgia Tech interdisciplinary research institutes that uniquely focuses on manufacturing research, development, and deployment. We help tackle the grand challenges of today's manufacturers and assist partners in moving innovations from the lab to the market. GTMI has a wide variety of facilities and equipment located on main campus for basic research, as well as on 14th Street nearby for more applied research and our advanced manufacturing pilot facility, which we're going to hear more about today. GTMI's mission includes education and workforce training, collaborative partnerships with industry, academia, and government, as well as thought leadership. GTMI hosts a lunch and learn series each semester. These sessions are excellent opportunities for Georgia Tech faculty, undergraduate, graduate level students, and researchers, as well as a global manufacturing community to learn and share advanced manufacturing knowledge. This fall sessions are held every Monday at noon. Today, we're both in person and streaming online via Zoom. We want this session to be interactive. So if you have questions, please jot them down. Or if you're online, put your questions in the chat window. And the speaker will address those at the end of the presentation. Today, I'm very pleased to introduce Dr. Zach Brunson, who will discuss in-situ sensing methodologies for powder-blown laser-directed energy deposition, which is an additive manufacturing technique. Unfortunately, Dr. Aaron Stebner was unable to be here and present today, but I'll be happy to connect you with him if you so desire. So Dr. Zach Brunson is a research engineer in Georgia Tech's Mechanical Engineering Department, working with Professor Aaron Stebner at GTMI's Advanced Manufacturing Pilot Facility. Prior to Georgia Tech, Zach was a graduate teaching fellow and a research assistant at the Colorado School of Mines in Golden, Colorado, where he received his Ph.D. in 2021 and a Master's of Science 2019 in Mechanical Engineering, studying theoretical and experimental mechanics of inelastic and anisotropic and asymmetric materials. Zach.
The standard mouthful for a Ph.D. thesis, right?
Exactly. Zach received his BS in 2013 in mechanical engineering from the University of Colorado in Boulder, Colorado, prior to pursuing his graduate degree, and gained experience working as a measurement field engineer in the petroleum industry. Zach's primary research focus include sensor development for process monitoring, part qualification in additive manufacturing systems, and theoretical and experimental mechanics of materials. In today's presentation, before we get into the technical talk, Dr. Brunson will give a brief overview of the Georgia AI Manufacturing Technology Corridor Grant, or the Georgia AIM grant. This grant will transform Georgia Tech's Advanced Manufacturing Pilot Facility into the Artificial Intelligence Manufacturing Pilot Facility, AI MPF. So there's a transformation that is going on that has begun and will continue over the next few years. This 24,000 square foot facility will more than double in size, as Georgia Tech and statewide Georgia AIM partners were selected as one of 21 Phase 2 awardees in the $1 billion Build Back Better Regional Challenge competition. In the main portion of today's presentation, Dr. Brunson will discuss powder-blown laser-directed energy deposition, for which mass flow of source material is a crucial parameter, whose measurement has proven to be particularly difficult, often with large errors. Dr. Brunson will discuss the challenges with this technique and their group's development of a four-mechanism sensing approach using coupled acoustic, capacitive, inductive, and piezoelectric techniques with the goal of reducing mass flow measurements errors, and eventually measuring the composition of mixed powder flows. Further, Dr. Brunson will share their group's development of a magnetic computed tomography system for in-situ quantification of defects in their layer-by-layer evolution, including formation, migration, and annihilation. Dr. Brunson, you may begin your presentation.
Thank you. So apologies from Dr. Aaron Stebner that he couldn't make it. He ended up double booked. He thought he could worm his way out of the other requirement, but he wasn't able to. So he's got me presenting on his behalf for the first portion of the talk. So we're going to talk about this Georgia AIM, and I'm actually going to start with a little video. Again, that's Georgia AI manufacturing. This should give you a basic idea, basic overview of what's going on.
It's time to start building up, building back, and building better. Right here in Georgia, we're working to transform communities through projects that will kickstart job growth and through the development of new technologies that will not only enhance America's global competitiveness, but also create a more robust economy long term. Our focus is the intersection of manufacturing, artificial intelligence, and innovations that drive economic development. This project is called the Georgia Artificial Intelligence Manufacturing Corridor, also known as Georgia AIM, with partners across the state. This corridor will bring together rural communities and urban ecosystems. Georgia's diverse universities and technical colleges. And together, we'll activate AI technology to ensure the resiliency of America's manufacturing sector from future shocks and global competition. Georgia AIM will revolutionize the industry economies of Georgia and the nation through the equitable development of the fundamental talent, innovation, and artificial intelligence. And that's from manufacturing sectors from energy and aerospace and flooring to food production. Georgia AIM will take on supply chain challenges and prove that disruptive AI manufacturing innovations can forever transform our country's industrial economy for the better. We'll support incubators to empower ideas from people that haven't always been brought to the table. Diverse communities will see the benefits of Georgia AIM, specifically underserved Black and brown urban communities and rural Georgia communities of all demographics, as well as active military and veterans, women, and people without a college degree. Our programs will reach every corner of the state of Georgia, from the biggest cities to the smallest towns. Education is also a key component for Georgia AIM, starting with students K through 12 and all the way through college. This will help us meet a critical business need to provide the highly skilled workforce and advanced technical training for the manufacturing jobs of today and tomorrow, especially as they relate to artificial intelligence. The AI manufacturing pilot facility in Georgia Tech will provide Georgia AIM in the nation with world-leading proving grounds for industry, government, and university partners to pilot trials and innovation of new technologies that will advance AI manufacturing and transition industry practices to new, exciting, and efficient ways of working. Collectively, Georgia AIM projects will develop the upskilled talent and high-tech innovations necessary for AI manufacturing to move our state and America forward. Innovating faster and stronger will not only create jobs, but will keep jobs right here in America. We're ready to build back better with the power of artificial intelligence.
All right. So that kind of summarizes what, half an hour's worth of info, right, in 3 minutes. So it's a good way to kind of get introduced to the idea of what's going on. Here's kind of the big picture figure. I'm going to break this down over the next 2 or 3 minutes here. There's a lot to take in. It all kind of starts with this grant from the Build Back Better. So that's the $65 million from the Economic Development Agency. That's being matched in part with $5 million from the state of Georgia, over $10 million from Georgia Tech, and partners in cost share. There's essentially 2 parts here. So there's the top portion here where we're looking at equitable development of talent and innovation. So this is essentially trying to help people learn, trying to help people get training, trying to help people become more familiar with everything that's going on. And then there's the actual deployment of this new talent and new innovation that we're fostering. So it's a 2-pronged approach. And it's been broken down into kind of 8 steps. The first one is the community engagement. So for the community engagement, we're looking at everything from K through 12 engagement and outreach up to startup incubation. From there, we're looking at kind of this step 2, which is this technical workforce development. Here, we're looking at the major thrust here is kind of a partnership between the Technical College System of Georgia and the Spelman College Innovation Lab. So the Technical College System of Georgia basically has 5 AI technician training studios that are going to be getting roughly $1 million each. And that's going to help them kind of build up that infrastructure. One of the examples here is semiconductors. Another one would be kind of your poultry processing. Then they're partnering, like I said, with Spelman College Innovation Lab, which is going to be developing extended reality. So the concept here is, let's say we have the poultry production industry that needs some kind of advanced training, some kind of AI engagement in their training. They can now reach over to Spelman College Innovation Lab, who's going to have undergraduates and graduate students working on extended reality programs. And then they can develop these new trainings, and then they can be deployed through this Technical College System of Georgia. Okay, so that's sort of that partnership that we're working on. That's, again, kind of point 2 here. Point 3, looking at underserved entrepreneurship activation. This is primarily being headed by the Russell Innovation Center for Entrepreneurship. They're developing the first of 2 mobile labs that are actually part of this whole series. Looking to move what they're doing in Atlanta out to the rest of Georgia. So they want to help those underserved communities to foster entrepreneurship. At the same time, UGA is working on a digital twin so that they can be kind of more at home and working with that mobile lab to try and give it as much support as it can have. Then we're looking at kind of number 4 here on the list. So number 4, that's this manufacturer cybersecurity adoption. So all of this is being taken in kind of as a holistic approach. So that includes cybersecurity infrastructure as a need for advancing advanced manufacturing and AI manufacturing. So the Georgia Cyber Center out of the University of Augusta is helping over 35 Georgia manufacturers roll out cybersecurity adoption as part of this kind of statewide thrust. Step 5 here, we're looking at kind of manufacturer engagement at a larger level. This is the Technical Association of Georgia, which is over 300 companies. They're looking at primarily this bottom half here, which is the deployment of that talent and innovation. So they're looking at internships, they're looking at job placement programs, and at the same time, they're also invested through industry feedback. So as we're doing what we can to try and help train new talent and foster new innovation, they're helping us deploy that talent and innovation, but they're also giving us feedback on how we can do better with that kind of first half of everything. Step 6, we're looking at this Middle Georgia Innovation Infusion. So in Middle Georgia, in that general region, there's only really one county that's looking to have any significant economic growth in the immediate future, and that's the community surrounding Warner Robins Air Force Base, which is kind of the center of the DoD's robotics research and application space. So there's going to be a second mobile lab developed to specifically serve kind of the Middle Georgia communities. And for this, they're looking at supporting specifically farmers and the agricultural industry and looking for ways to help them apply, not just to apply AI, but to apply it in an intelligent way, in a way that's going to help them improve, as well as coupling it with robotic solutions to some of the problems in that agricultural industry to kind of help economic growth in Middle Georgia. Step 7, we're targeting specifically Southwest Georgia ecosystem. For this, we're looking at automation solutions, primarily for poultry production. That's one of the largest thrusts in Southwest Georgia. But we're also looking for other manufacturing, as well as job support in the region. Again, kind of focusing on a specific region of Georgia here. That's the first 7. The 8th is kind of what I'm going to talk about really for the rest of the talk, so I'm not going to go too much on this slide. So the 8th is what we're doing here at home at Georgia Tech. So step 8 here, or part 8 of this multi-part approach, is the AI manufacturing pilot facility, right? So AI MPF. So for the AI MPF, This is a lot to take in. I'm going to kind of step through it from the top and work my way down here a little bit. In the upper right-hand corner, it's kind of a bird's eye view of what we have right now, about 2/3 of the space that we have right now. It's a little over 20,000 square feet. It's a reconfigurable R&D space, innovation space. It's essentially a manufacturing high bay. It's off of 14th Street. So it's 3/4 of a mile from where we're presenting this right now. The goal here for the facility that you're seeing as it stands is really supporting industrial, academic, and government stakeholders at the moment. The technologies that are included, I'll just kind of go down the list here, not entirely exhaustive, but we're looking at metal additive manufacturing, precision machining, robotics, non-destructive testing and evaluation, specifically targeted at inspection for the former two that we were just listing, metal feedstock production, heat treatment, and characterization. So trying to capture most of what you need to help get these more advanced technologies off the ground in an actual application sense for being able to create parts that can be qualified, they can be certified, as well as all of the associated aspects needed to help with that qualification and certification process. The vision and mission sort of in part now and looking forward towards the AI MPF side, right, is to support scale up and translation of basic research into implementable technologies. So the basic idea is we have 3D printers. 3D printers can make a shape, but that doesn't mean that the shape is actually able to be put in a car, a plane, or something else where it's going to go ultimately in industry. Not yet. So we want to be able to take what exists, we want to be able to translate it to actual manufacturing facilities and try and answer the questions needed to do that. Providing a demonstration facility for partners to co-develop and integrate new materials, processes, digital models, so to de-risk new technologies. Somebody says, hey, can I make this part on this system with this new material? That's the question, the new material in particular. We have what we need in-house to actually try it and see, is it feasible, and start answering some of the base fundamental questions to give them a leg up to then see if they can actually deploy it on their own as either a new startup or as an addition to an existing manufacturing program. And then kind of this third portion here is to enable training and upskilling of a competitive skilled workforce on next generation advanced manufacturing technologies. So this is, I mean, we're a university, right? We work with undergraduate students, we work with graduate students. So making sure that they have the training that they're interested in getting, additional training, even beyond what would be their standard coursework, but also with moving into this AI MPF thrust, trying to bring in people from other communities to get training, to work at our facility and learn the equipment that we have to see, can it do what I need it to do? How do I actually use this equipment to do what I want to do and to become more skilled workforce? So the future AI MPF, AI manufacturing pilot facility, is that it's just over 20,000 square foot right now. We're going to approximately quadruple that. So we're going to be moving up to about 85,000 square foot for the AI MPF space. Eventually, we'll look at this here in a little bit, but part of that is we want to be able to automate moving samples, specimens, products from one location to another. And to do that, we want to try and use automation. We want to have robots essentially moving things from one place to another. Robots have issues with walls, halls, and doors. So we're expanding the space and we're tearing out a lot of the walls, halls, and doors, right? We're going to use this as a proving grounds for innovating and de-risking AI materials and manufacturing technologies. So here's kind of the big picture image for this. 5 themed areas in the space. We're going to have a metals region, looking at AI for metals tech. We're looking at polymer composites, looking at high temperature composites. Primarily, that is your kind of ceramic matrix composites space that we're looking at. Then we have a materials handling and supply chain section, and then a characterization, synthesis, and recycling section. So that is kind of a lot lumped into that last section. It may actually be one of the larger ones here because we need to characterize everything as we make it. So kind of looking through this picture here a little bit at a time, developing new materials, recycling old materials, basically trying to construct samples that can be used to test and qualify different processes or materials or procedures in multiple ways. So we're looking at your monotonic loading here in tension. We're looking at fatigue loading. We just got some new fatigue machines in. We're looking at different processes, different materials. So over here, different material, different process, different way of making these samples. Samples will get queued in the line and go through a similar characterization path. So the idea is trying to move equipment and parts from location to location. To do that, we're going to need some level of automation, right? So we're looking at having robots. We're going to have a mezzanine that's going to be built over this kind of 85,000 square foot space. That mezzanine is also going to serve not only for office space, conference room space, but also for support for arms like this, right? In order to allow us to move equipment from one station to the next, right? In tandem with moving the physical pieces around, we're also going to have infrastructure installed to help move data around, to catalog data off of the different machines, to be able to record the print parameters that are used, the machining parameters that are used, to record the atmospheric conditions, for example, in a printing chamber. All of this information to be recorded and moved up to a cloud system, to be able to then be read off online remotely, or to be tagged with the individual parts that are then going to be moved around remotely. We're going to have some spaces that are going to be clean room spaces. So we are going to have some walls, for example. We can have machines like this built in place to transfer equipment or pieces through those walls, or using the walls as space to move parts around to try and keep the floor space as open as possible. So just kind of examples of what we're looking at for handling parts and doing the automation for that. So this is the current space right now. If you were to go up to 14th Street, it would probably look, it would look almost exactly like this. This is what we're looking at kind of for the future moving forward, right? That kind of wraps up most of this introductory portion on the Georgia AIM. I would take a few questions now if there are. I see what I can answer. Might end up forwarding you to Aaron to answer some of those. He and Dr. Kerfus are kind of the big wigs in charge of this, and they're going to have a lot more detailed answers than I will. So if there's any questions here before I move on to the next part of the talk?
Yeah, I think it'd be a good time.
Yeah, so first of all, thank you. As far as the AI is in the manufacturing is going, I mean, there's only so much you can learn from one facility. So is the vision to this facility is going to be created all across the country, presumably. Can you?
So this would be the AI MPF is going to be here on site. So this is kind of one of the core pieces to try and answer questions. Then we have the mobile facilities going out and trying to take what we've learned and what we found ways to apply. And I say we, that's Georgia Tech here at the AI MPF, but it's also going to be the other universities, the other colleges, Technical College System of Georgia, that are all involved in this as well. So it's not just here at Georgia Tech, but it's all across the University System of Georgia, the Technical College System of Georgia that are kind of involved. So that already gives us some real estate elsewhere in terms of being able to interact with other communities. I don't know if that answers your question entirely,
Okay,
but
partly. And
okay.
so the sensors that you're developing that are going to be recording things inside the manufacturing milieu, those are going to be distributed so that you can learn from all the different locations that are implementing these manufacturing.
Eventually. So I'll talk about some of the sensors that I'm developing here as the next talk. AI MPF, the facility here off of 14th Street would be the test bed. Once we know that it is working, that we're able to record reliably the information that we want to record, then that sensor can be deployed to similar test beds around the state. Does that help answer that question?
Yeah, and then when you apply all those sensors, then is that learning happening locally going to be amalgamated somehow so that you can have more robust?
I mean, that's part of the AI part of AI MPF is once we're able to start collecting a much larger collection of data on multiple machines in multiple locations, that gives us what we need to start applying some of the AI tools in our tool belt, right? So yes, that is a few years down the line before we can really sink our teeth into a lot of that kind of data, for example, before we really have everything deployed, before we actually have a large enough data set. But yes, ultimately that's the goal, with coupling AI kind of with that manufacturing side.
Just some perspective, I mean, this was the single largest grant for Georgia Tech, and would you clarify that maybe?
Georgia Tech, yes, that's what I've been told. I don't know all the details,
Single
but
grant.
yes, yeah.
So that's how massive this is.
It
I saw
was,
65 million, but then I saw
that's also,
80 million.
so 80 million is if you add it all up. So 65 million from the Economic Development Agency, 5 million coming from Georgia State, that gets you 70. And then Georgia Tech, as well as cost share partners, is over 10 million. I think it's in if you would cold hard cash, it's around 11. But if you account for in kind, then I think it's over 100 million actually.
This is massive.
Yeah, it's a large thrust. I mean, we've got a large anchor here, but it's statewide. It's not all just with Georgia Tech. It's a statewide thrust. So, all right. I'll go ahead and move on to the next part of the talk then. Check time here. I might have to skip a slide or two, we'll see. So this portion of the talk, I want to go through kind of some of that sensor development that I'm working on. So looking at specifically in situ sensing methodologies for powder blown laser directed energy deposition. I know that's a mouthful. It'll make sense in a second here if you're not already familiar with it. So quick roadmap, 5 things that I'm really going to go through. I'll kind of get everyone familiar with this powder blown DED that I'm talking about. I'm going to go through a unique problem, which is this mass flow, and then the sensors that we're developing to try and solve that problem, as well as a unique opportunity for defect detection, and how we're tackling that also with sensor development. So directed energy deposition, or DED for short. I'll probably use DED for the rest of the talk, just to save a bit of time. So I'll do a brief intro here with additive, and then LPBF so that I can compare and contrast with DED. So additive manufacturing, there's a lot, right? There's a whole bunch of different kinds of additive manufacturing out there. I'm not going to discuss them all today. I'm specifically going to look at those with powder feedstock and using lasers for energy introduction into the system, right? And of those, I'm going to be looking at powder bed methods, and I'm going to look at DED methods specifically. So I'm just going to kind of isolate myself in a small corner of additive for today. So laser powder bed methods. Basically, there's several components here of it. We're going to go through them real quick. We have some kind of powder container that's basically allowing powder to be fed back up. We have the descending build platform over here on the left that's going to lower down to receive the next layer of powder. We have a recoder blade that's going to swipe that little pile of powder over. Once that stage on the left drops down, that creates a new layer of powder. Our powder bed is basically all of those layers of powder added up. Our part is specifically where we've been hitting with the laser and melting that powder, fusing it together. So here's what that generally looks like. Video should play. There we go. So the stage is going to drop down, recoder blade comes across, fills the powder bed with the next layer of powder. Some systems will actually have a second pass that'll come by and clean up the first pass. So that's what we're seeing here. And then we're also getting ready with the next bit of powder. Laser comes through and it's going to melt. Here's what that actually looks like in real life. So we're seeing multiple parts being printed. The laser's jumping around, that's generally your print strategy. That's part of the data that we would have to be recording, for example, is exactly where the laser's hitting and when. We have the powder recoder blade comes through, swipes down, next bit of powder, and then we can start printing again. Powder blown laser DED is a bit different. It all centers around the print head rather than a powder bed. So the print head here, I'll go ahead and let this play kind of behind me. The print head here feeds powder down through some of the cables or some of the lines. And then when the powder comes down, we're going to have a laser that's going to come down in the center. The laser is going to locally melt. The powder is going to fly into the melt pool. And then here's what that looks like kind of in real life, if you would. One of the benefits of DED is that we can actually work with larger parts because we're not confined to the size of a powder bed. We also don't have all of the additional powder around, so we can manage to be a little bit more conservative in our use of powder. We only need as much as what's going in the part. We can also incorporate 4th and 5th axes. That means that we can change our build direction during the print. This helps to mitigate the need for things such as support structures that you might need in a powder bed system. Right, so there's more variables at play here in a DED system. Our specific DED test bed is the Optimec 860. It has an enclosed argon environment, 4 powder feeders with a mixing chamber, an optional 4th and 5th axis, and a 2000 watt laser. The material systems that we are specifically studying here, this is our test bed primarily for new materials, novel materials, or materials that we've had trouble with elsewhere. Right, so we're looking at refractory alloys, things like molybdenum, tantalum, niobium, and new alloys of those. We've got a grad student working on some molyrhenium alloys, for example. We've got shape memory alloys such as nickel titanium and its variations, nickel titanium hafnium, some new alloys with nickel titanium copper molybdenum. We've got functionally graded materials. We're working on printing, for example, from titanium to molybdenum, going from this material that's lightweight to something that is a higher temperature resistance. There is a unique problem that shows up though. It has all these benefits that we can play around with, such as changing materials. It makes it really easy to do graded materials, but we have the issue of mass flow monitoring. So why do we need to monitor the mass flow? It's not guaranteed. Right? You may try and say, this is what I want, and you're not actually going to get what you're asking for. That could be because you have Hopper calibration drift, you have powder compaction within the system, which is changing the way that it's behaving. You've got flow obstructions, you have leaks, among many other things that can mean that what's actually coming out of that print head is not the same as what you're asking for over by the powder hoppers. Compromised mass flow can affect your repeatability. It can also ruin parameter space studies. That's what I'm showing as an example over here. Those in the red box, something happened and clogged the lines and powder flow changed. We didn't realize it until 3 things had been printed. So somewhere in here, we don't know exactly which one, the mass flow wasn't what we were asking for. So the parameter space study was kaput. We basically started it over. We could solve this if we had feedback controls. We can monitor mass flow accurate enough, fast enough to be able to feed it back in and use it for feedback control. The Optimec powder flow system, as I kind of said before, we've got 4 different hoppers. Here's what they look like. Powder starts in one of the hoppers. It's going to move down into the powder pickup area, where a rotating auger is going to deliver the powder into a carrier gas. Specifically, we use argon. It's going to go up through all the lines into the upper left-hand corner here. It'll go through a flow mixer. From the flow mixer, it will proceed to the print head. At the print head, the flow gets divided again. So it gets mixed together here in the mixer, and then it gets divided again at the print head. It'll either feed the powder into separate nozzles. One of our print heads uses 4 separate nozzles that blast the powder as 4 streams into each other, kind of canceling the X and Y momentum, so you just get downward. And the other one is an annular nozzle. In that case, we're distributing the powder kind of around the annulus through that division. So what we're doing to try and get a better handle of what the mass flow is developing multiple sensors. I'll kind of go through them all here. The transitions might feel a little abrupt, but there's 4 different classes. There's an acoustic, capacitive, electroinductive, and a piezoelectric. For the acoustic sensor, we're using something called acoustic emissions. So you have some internal mechanism that generates an elastic or an acoustic wave in a solid medium, right? That could be a crack initiation, propagation, phase transformation, twinning. Something happens inside. If I'm listening on that surface of that solid material, I'm going to hear some kind of acoustic emission. That's where the term comes from. The solid medium radiates energy as an acoustic wave. So that's what we're calling acoustic emission. We're going to use that concept, right? We're not the first people to do it. As powder flows down the tubing, it obliquely impacts the inner wall. That's our event. The elastic wave is generated and it's transmitted through the tubing. It produces this acoustic emission, so we can listen with standard acoustic emission sensors and we can correlate that to those impacts. The acoustic emissions are essentially related to the kinetic energy of the powder particles impacting the wall, which can be correlated to the mass and velocity of the individual powder particles. Here's the sensor that we're going to be testing. It was one developed by NIST back in 2018. It captures this acoustic emission data, correlates it to mass flow. It is an insert device, so it's not something we can clamp on the outside. We actually have to break the line somewhere and insert it into the flow. The reason this is done is to introduce a steel tube, so the impacts are more elastic. So we're conserving a bit more of the energy, and we can optimize the acoustic connection between the sensor and the tube. So there's no real air gaps. There's no kind of bonding. We're just pressing that sensor up against the backside of the steel tube. They found a strong correlation to mass flow when they did the initial test. You can kind of see that over here. R squared value is pretty good for titanium, but if you look at point-wise deviations, we are looking at seconds down here on the bottom, but you notice that they're 50-second transitions. So that means that I may be accurate over a minute on average, but if I'm trying to use it for feedback control, then I need something closer to second accuracy. Point-wise deviations are on the order of about 10% or less. So not horrible, but not great if you're actually trying to use it for feedback control. For steel powder, they got a slightly better correlation, but they were still looking at a similar point-wise deviation. They had some interesting observations, which kind of reinforced the need for developments in this particular sensor space. They found inconsistency in the mass flow for a fixed Auger speed. So there's 5 instances here that I'm highlighting where the system is still saying, I want this mass flow, but you're seeing that we have these dips and these rises that are significant in terms of the mass flow, even though we're not changing any of the controls. So this is why we want to have feedback in the system. We also have unrepeatability for the mass flow for a given Auger speed. That's demonstrated here between the 2 green. It's the exact same setting at 2 different times, and they're giving 2 different average mass flow outputs, right? Which is on the order of about 10 to 12% difference here in those mass flow outputs. So we're going to take, I guess I should step back a slide. So we're going to take what they've done, we're going to reproduce it. We're going to use that as our starting platform. And we're going to introduce these other sensors to give us more data so that we can couple those data streams together and try and improve their measurements. So the first one is going to be working with capacitors. So a little bit of background on capacitors, or at least a refresher. You've got your 2 conductive plates. Those are going to hold a charge. You've got a dielectric medium, doesn't conduct the electric current, but it does allow the electric field to permeate through it. And charge buildup on the plates is going to generate an electric field across that dielectric medium. Cool. So what's important about the math? Here's all the parameters involved in this. The one that we're mostly interested in is that dielectric constant. So the dielectric constant is a property of the material between the plates. So if I can try and solve for the capacitance, I can solve for the dielectric properties, I can solve for what's between the plates. We're going to put the powder between the plates. The idea here is that the dielectric constant of the powder flow is a mixture of the carrier gas properties, the powder properties, and the volume fraction of powder in the flow. So as the powder flow rate changes, the capacitance of the sensor changes. That gives us a digital signal that we can then use to feedback either for control, or we can couple it with another data stream to try and improve the error. Here's the actual prototype, or well, I guess a CAD model of it. The actual prototype is in pieces right now. I'll explain in a second. So the capacitive insert device, to avoid signal dampening, we can't just put the plates on the outside of the tube. The tube essentially overrides most of what's going on as far as the dielectric is concerned. So we need to get the plates inside. That's why we're working with an insert device. We've got 6 plates. This gives us a larger capacitance to help amplify changes in the dielectric constant. We can't do more than 6 plates because if they get closer together, then we end up with them too close together for the powder to flow between. So we had to kind of play some optimization games, make sure that there's enough space for the largest powder particles we expect to flow through. At the same time, we can't change the cross-sectional area of the flow because that changes the velocity of the carrier gas fluid. And if it slows down, then the powder falls out of entrainment, and then we just have a powder plug that doesn't help anybody, right? If we run a quick sensitivity analysis using steel powder as an example, 38% powder in the flow volumetrically gives us a capacitance of around 2.8 nanofarads. 48% gives us around 4.6 nanofarads. So it's pretty small capacitance that we're working with. But as far as the sensitivity of our circuits, we're expecting to be able to read this. We are hoping 10 picofarad sensitivity with the circuits that we've set up. And so that should give us pretty strong resolution in terms of this kind of volume fraction of the powder flow. Flow analysis. We considered a possible reduction in the velocity when we ran our basic flow analysis. You can kind of see that up here. There's a minor dip in the flow velocity. We actually then printed the part, stuck it in, and checked. Does the powder slow down? Does it fall out of entrainment? Nope, it was fine. Except for a tiny little pinhole leak somewhere in the system. And we didn't find it for a couple weeks. And then we had a little pile of powder underneath the device. by the time we actually found it, cleaned that up. We tore it apart to try and find out where that little flaw was. We're making the second prototype now, hoping in a couple weeks to plug it up and actually start collecting data. Right, so that's sort of where we are on the capacitive sensor. The next one that we're looking at is inductors. So quick refresher again. Inductors, you've got a coil of wire, transmits electric current, core material, which affects the magnetic field generated by the inductor coil. The current flowing through the coil generates a magnetic field. All right, what happens if we flow powder through this inductor? Right, inductance is governed by everything here. This is kind of starting to rhyme with the capacitance sensor. All right, we have this kind of permeability of the core parameter. It's a material property. As powder flow rate changes, well, not exactly what we expect. We have a problem. This change in this magnetic parameter here is generally very, very small. It's only going to be significant for ferromagnetic powders. Right? So we can't actually use the same method that we did with capacitors if we want to play around with inductors. The solution here is to cycle the current. If we cycle the current, we're going to create a changing magnetic field. Changing magnetic field is going to induce eddy currents in the powder particles, which means that we're going to have a magnetic field produced in the powder particles that combats the magnetic field that we're generating. That's something we can measure. It's independent of whether or not we're ferromagnetic or not. So that allows us to play with pretty much every metal powder we want. We're going to take inspiration from more conventional inductance sensors for your liquid flows, where we have two different coils, and then we have a way of measuring essentially a potential difference, either plates or pins across that flow where the magnetic field is exciting it. So here's what generally the sensor system would look like. We're looking at three different options here. So when we created this setup, we realized there's three different ways that we can excite it and measure what's coming out the other side. We expect the sensitivities to be different. We don't know if they will be different for the different powder flows or if they will uniformly be different, in which case we just pick the best one and run with it. The first option is to measure the effect on the magnetic field. For this, we're going to excite one coil and listen with the coil on the other side of the flow to see how that magnetic field is being changed by eddy currents generated in the powder. The second option is to activate both coils and listen with the plates. So that's that coupling between your electric field and your magnetic field. An oscillating magnetic field is going to stand up an oscillating electric field. Powder flow is going to interrupt the oscillating magnetic field, so it'll interrupt the oscillating electric field. We may be more sensitive with that, or we may not. We'll find out when we actually test it. Option 3 is to excite the plates, generating a standing electric field. In this case, we have a standing electric field. We have powder particles that are going to fly through it, which are going to turn into little dipoles. Right? We're going to play around with Gauss's law here. So we have little dipoles. So you have positive charge on one side, negative charge on the other, zooming through the system. In this case, we're going to try and listen with the magnetic coils to see if there's an induced magnetic field that's strong enough to pick up with them from the moving dipoles. The last of the sensors that we're introducing as new sensors is this piezoelectric impulse sensor. So for this, it is a low profile insert device. Each of these have been an insert device. We haven't been able to find a way to clamp something on the outside. So we have to do an insert device. Let's see if we can make one low enough profile that we could potentially put it on each separate nozzle in the print head if we've got multiple nozzles. So that's what this was targeted for. We use a piezoelectric sensor in an angled bend, which gives us an increased number of impacts. And we're essentially sampling the flow. We're not measuring all the ones before, we're measuring everything in the flow. This is going to be a subset of the flow. So we're sampling the flow using direct impacts, correlating it essentially with the number of particles flowing with their momentum, which is essentially their mass and velocity. All right. So more holistic approach, looking kind of at all four here at once. We're looking at multi-physics approach. We have electromagnetic sensors, which are sensitive specifically to the volumetric density of the flow, kind of your mass flow rate divided by your velocity. We have the flow composition. So if I change what the powder is, I'm going to get a different signal strength. So I can actually tell if I'm flowing, for example, or at least the hope is that we can tell if we're flowing steel versus titanium, for example. The mechanical sensors on the right are sensitive to variations in the flow's kinetic energy and particle velocity specifically, right? Goals are to compare the measurement errors of each individually. There may simply be one sensor that dominates over all the others, and that solves the problem. We're looking at NIST as kind of our standard that we're basing everything off of, seeing if we can improve that. If we can combine methods to reduce the errors in their specific case, then that gives us an advancement as well. Once we can reduce the errors, the question is, we still have extra parameters up here that we're measuring, more than just what's going to give us mass flow. Can we use that to identify composition of mixed flows? We have 4 powder hoppers. We can mix them. I can put nickel in one, I can put titanium in the other, and I can flow them at different ratios to change that shape memory effect in what I'm printing. I want to do that reliably and have spatial variations across the part. I need to know what the composition of my flow is where I'm printing. So that's the next goal for this project. Once we can reduce errors in general mass flow, try and divide it up based on composition. And in all of these cases, integrate it back into some kind of feedback control system, so we can actually improve reliability of the system overall. So that was sort of the mass flow problem. Now we're going to look at an opportunity. We have a unique opportunity when it comes to DED, which is looking at defects and additive manufacturing. I'm going to start with the long history, and I'm going to do it all in basically a slide, or maybe like 2 bullets, right? We have this ever-present set of questions when it comes to additive manufacturing. Does my part have porosity? How big are the pores? How many pores are there? Where are the pores located? This is the question that everybody asks when they print a part, especially in metals 3D printing. The impact, the reason everybody's interested, can I qualify this AM part? And can I certify my specific AM process? If I don't know how big the pores are, where they are, if they're in a critical location, how many there are, then I can't actually say what the fatigue life is of this specific part, or what the fracture toughness is for this specific part, right? So that's why we're interested in defects. We haven't solved the problem yet. Current defect detection pursuits, right? Current approaches all show some kind of promise, but aren't there yet. We have optical melt pool monitoring, melt pool thermography measurements, layer-wise thermography measurements, acoustic emission methods. All of these are trying to quantify when a pore is formed and where it's formed and how big it is. Everything in the methods up above is trained on X-ray computed tomography data or serial sectioning microscopy, which is what you're seeing off on the right here. X-ray CT data is on the left in section A, and serial section microscopy is what we're seeing in B, right? Where we're seeing physically where the pores are. Problem is, all of these are defects in the final part. So we're listening for the events that say, hey, listen up, a pore has formed right here, right now, it's this big. But we're only checking for the pores that survive till the end of the final print. So we have a disparity between our measurements and the data that we're using to train those measurements to give us an actual useful piece of information. To kind of drive that point home, here's 2 videos for actual defect histories. So on the top, we're looking at that first layer that's being printed in a powder bed system. The laser is melting the powder. You're seeing that dark region is basically where the powder is actually becoming liquid and then eventually solidifying. Anything light in that dark region is a pore. So you can see the set of pores that just formed at the end of that particular path of the laser. The second video on the bottom starts with that as the bottom layer and then prints another layer on top and asks what happens to the layer underneath. So this was all done at a synchrotron facility with high brilliance X-rays, so high intensity and high number of photons. Not something you can necessarily do in a lab, but what it shows us is some of those pores were destroyed, some of them moved, some of them fused. It is not a fixed piece in the part. It's not a fixed feature. It can move around when you start printing with the next layer. So defects formed in one pass can be annihilated in the other, shift position, change size, or combine with neighbors. So why not in operando X-ray tomography? Why don't we do what we just watched in every 3D printer, right? There's no powder bed in the way for DED, so why not? Tomography, every layer would provide transient defect data set. This is what we need to try and calibrate all the other methods. So why not? Because it's very expensive, it's very time consuming. There's not enough space in the machine to put a football stadium sized system inside of a 3D printer. And there's also some radiation and safety concerns. I don't want to be by it if you're doing it. All right. The time consuming aspect, if we try and downsize it to a lab X-ray system, we're looking at something on the order of 5 to 10 hours per layer to get a scan, which interrupts the entire printing process. Right? So it's not feasible either at a synchrotron to do it actually in operando or in a lab X-ray system. So here's our opportunity. We're going to try and exploit it by playing around with a little bit of a different section of physics. So we're going to play around with magnetics and look at magnetic tomography, specifically eddy current magnetic computed tomography. So a little brief, how does XCT work? Right? We basically have our X-rays that are coming from some X-ray source, passing through a sample, hitting the detector. That's showing us some amount of attenuation, kind of seeing separate frames being shown here on the bottom. The information comes from the X-ray attenuation through the sample. We rotate the sample 360 degrees. We can use that information to reconstruct a 3D model of the part, right? How? One of the standard methods is back projection. So we basically have a specimen here, a cubical specimen. We have a cubical cavity in that specimen. We're going to take a section through that specimen right about here. That's going to be our sectional plane. We're going to excise that sectional plane, and we're just going to look at that. So we're going to kind of do some imaging on a line rather than imaging in a full 2D frame. So here's our sectional plane. Then we're going to throw some X-ray radiation across that sectional plane. And we're seeing essentially this radiation intensity profile over here. So we have less X-rays come through where you happen to have material. We have a little bit more where there happens to be a pore. This is that radiation profile. A back projection basically says we take that profile and we're going to project it back across everything. Okay? We're then going to take all of these projections, we're going to do them at multiple different orientations, and we're going to superimpose them. As we superimpose them, everywhere that you happen to have a slightly smaller amount of attenuation will overlap at the same point, which should be the point of wherever our defect happens to be. Right? So that's generally your back projection method. It doesn't have to be done with X-rays. We're used to doing this with X-rays, but there are other methods that have been used to collect the information to back project and create a reconstruction like this. Right? I can then take the negative of the image. That's going to give me what you're seeing here. So rather than the attenuated amount, that's going to be the amount that was preserved. We can then stack all of these up and recreate a 3D of the original part. My videos are lagging a little bit here. So we'll go ahead and kind of jump forward. But that's your general back projection method, and it doesn't matter if we do it with X-rays or not. So we're going to do this with eddy current sensing, right? Eddy current sensing, we have a driving magnetic field, generates an eddy current. Basically, we're playing around with Faraday's law here. The eddy currents generate an opposing magnetic field. This is essentially Biot-Savar's law here. The relevant properties in both cases, we're essentially coupling these two laws together, so we end up with the material's resistance, right? So this is voltage from Faraday's law, and we end up with current in Biot-Savart law. The connecting factor here is going to be resistance. The magnetic permeability in the Biot-Savart law is also relevant, but since we're going to be oscillating that magnetic field, it comes in a close second as opposed to the actual primary method. So if we don't have ferromagnetic materials, it's not that big of a deal, right? Early efforts demonstrate the efficacy of using eddy current data to create a tomography image. So this came out of Russia in 2000. The setup here, they use 16 fixed coils, 5 centimeter diameter coils. They created a 35 centimeter diameter arrangement. The application space here that they were working with was medical. So their experiment used saline-filled phantoms, and their aim was to map the regions of higher and lower salinity. Right? So essentially looking for, say, organs in a person's torso. The reconstruction method that they used was a nonlinear back projection. So X-rays travel in a straight line. That's why we get to do what we just saw on the video. Magnetic fields, not straight. In almost any stretch of the imagination, they're not straight. So we'll have to use a nonlinear back projection to follow the field lines back to where they would have essentially come from, but then everything else gets to play out the exact same way. So our magnetic computed tomography method, the setup is kind of over here on the right. A single frame is going to use an excitation coil that's very, very large. The sample, and then an eddy current sensor grid, which is a lot of little tiny coils or a lot of little tiny Hall effect sensors. Each frame comes from an eddy current reconstruction. We rotate the sample 360 to create our 3D. Right now, we're working on a proof of concept. So we're basically looking at a single Hall effect sensor. We're going to raster the sensor over an XY grid. This gives us testing of different sensors at a lower cost. So we can try different sensitivities, different types of sensors, see what works best during this proof of concept. The experiments are currently being performed in an Okuma Multis CNC mill turn, where we're going to rotate the sample with the lathe chuck and then raster the sensor with the mill head. Here's the samples that we have machined. They're 19 millimeter diameter cylinders, 25 millimeters tall, 6 different feature geometries, and we're working with copper, aluminum, and ferritic steel. So that gives us 2 different resistances for the materials that are non-ferritic, and then we have a ferritic steel to see what mayhem it wreaks. So this is going to make in-operando tomography possible. It resolves the problems with XCT, so we end up with a lower cost system than having to go to a synchrotron. We're looking at less than maybe upwards of 2 minutes per 3D scan, which is much better than 5 to 10 hours with a lab-based XCT system. It's adaptable. It'll be a compact form, so we can deploy it between layers so that we're not interrupting the printing process, and it's radiation-free. The initial expected voxel size will be 100 microns, and then targeting up to 75 millimeter thick builds with this system. So quick conclusions here, since I know I'm almost out of time. We looked at that unique problem of mass flow monitoring and sensor development using 4 different systems: acoustic, capacitance, inductance, and piezoelectric. And we looked at the unique opportunity in DED of defect detection and specifically looking at a magnetic computed tomography sensor development. So that's sort of my quick conclusion. I'll go ahead and jump to my question slide and see if anybody has any questions.
We have any questions, in person or online? Dr. Brunson.
What you got?
Thank you for your presentation. Using the tomography, I mean, whether X-ray or the magnetic fields. So, is it possible to just measure, I mean, control fault or detect faults in situ and in real time? Because you are getting image, and for example, to detect image and give feedback, you have to do, for example, some image processing.
Yes. So for XCT, no, there's just not a chance, right? I mean, if I did dwell fatigue studies with these little 1 millimeter diameter samples, and it was taking us anywhere from 8 to 64 hours to get a scan, depending on the resolution we wanted. That doesn't give you real-time feedback, right? The hope here is maybe not real-time feedback, but not interrupting the printing process too severely, right? If we can get a scan in under 2 minutes, then we're not dissipating all the heat that was built up in the part, we're not interrupting the process terribly, and we're able to collect data that we can use to train all of the other methods. The other methods could be used as a feedback control. Oop, a pore formed here, we should do this on the next pass to try and erase it. Problem is, we don't have a lot of data for how to erase them either, which is kind of why we want this layer by layer tomography without interrupting the physics of the printing process too terribly much. Even if we can't use feedback control, it gives us data we can train all of the other systems off of to make them more reliable. Yeah.
I had a question or two. One was for making alloys, I guess, with this DED, because you mentioned some of the sensors are used for composition, being able to tell what, the titanium powder from a
Nickel
powder
or steel, yeah.
So is that the idea, to be able to quantitatively, predict the alloy composition by using the sensors in the mass flow?
Eventually, yes, it would not be enough. And that's because as you print, you're introducing energy. If you have different materials, they evaporate at different temperatures, they have different vapor pressures and everything. So for example, if I want titanium with 6% aluminum, 4% vanadium in a final part, and you start with source material that is 7% aluminum, because that much of it just goes out into nowhere, right? It evaporates away, deposits somewhere on the inside of the machine. So it's going to be a combination of the feedstock that's being dropped in and all of the thermography data we can collect in terms of what's the temperature of the melt pool, how big is it, how long does it stay that hot, all of that information would have to be coupled with it too. So it wouldn't be the end of the sensor program. We are currently looking at a full thermography system as well. I didn't present on that. That's another one that I'm working on right now as well. Once we have both of those, we could couple them, and yes, the goal is eventually, maybe a few years down the road, to be able to say, here's what the composition is at this location in this part. So we can do functionally graded materials and be able to qualify the parts.
So to say, like if you have the starting composition in the powder,
Mhm.
then you have these parameters.
Mhm.
Your sensor data could help inform you about the alloy composition in the final part,
Yes.
essentially.
Yeah.
My second question, for the Optimex system itself, the factory system, does it have any type of sensor capabilities
So
built in, or?
no, there's an auger that spins and we correlate the speed to the mass flow. So everybody basically reports their mass flow in RPMs, right now, because that's just like, here's what we used. You also have the flow rate of the argon, which affects it as well. Not so much, but it does. Basically, right now, we put a scale in there, we put a cup on the scale, we blow some powder into it, and we calibrate the system right before we print, and we calibrate it after, and we hope we stayed between those two for the whole print. That's the way we do it right now. So right now, there's no actual feedback control. There's no quantifiable measurement of mass flow. We have RPM, and that's it. Yeah, what you got?
What kind of resolutions do you hope to achieve with the magnetic tomography for pore size?
So we're looking at 100 micron voxel size, 100 micron, 100 micron, 100 micron, based on Hall effect sensors that are out there right now, what we can play around with. We go to the silicon level, we can pack them a little more densely. We may be able to make the sensors slightly smaller. One of the benefits of eddy current systems is that they can sense things smaller than the individual voxel. So if I have a crack that's very thin, that crack has interrupted any ability for current to flow really across that region, right? It doesn't have to be this big to interrupt the flow. It can be paper thin or less, right? So small features will still show up. Now, if the entire feature is within a pore, you have the problem of the magnetic field essentially is generated around the feature. So you cancel yourself out. But if any aspect of the feature extends beyond the size of a voxel, then we can say there's something there. Maybe not how big it is, we can say it's there, and then we can say that it's not, for example, in the next one. So that's the resolution that we're looking at. It's not a hard answer. That's what we're looking at right now. With further development, we may be able to improve on that.
And how indifferent it is for like different compositions?
Compositions, we're not sure. We're going to actually have to see. One of the problems is going to be your skin depth, so the penetration of the signal, which is a function of the material and the frequency at which we oscillate the magnetic field. So we will probably end up with a different frequency for a different composition in order to try and get an improved skin depth. That being said, the skin depth is not how far the magnetic field permeates. It's how far it permeates before it falls off by a factor of E, essentially. So we can go 2 or 3 skin depths if our sensor is sensitive enough on the other side of the system, right? And if the magnetic field is strong enough on the front side. That's why we're playing around with a coil that is bigger around than my fist, and we're playing around with sensors that are 100 microns by 100 microns. Is we have a massive excitation coil to get through everything, and then a sensitive sensor to pick up what's left on the other side. Does that sort of answer your question? Okay. Yeah.
It's maybe a novice question, but has this magnetic computed tomography, has that been proven, I guess, the theory of it, and has it actually been shown in publications and that type of thing? Or is this
There's
something
one publication that's tried it. They did get a successful result. So that's what we're seeing right here. This was their setup. Here was their reconstruction. So they were able to isolate the different salinities of 0%, 1%, 3% salt in that solution. It was slow. It was not as high of a resolution as, say, an MRI machine, right? So for medical purposes, it wasn't relevant. It was only published in a lesser known medical journal, and nothing really came of it, right? There have been similar systems that have played around with impedance, that have played around with resistance, capacitance, et cetera, to create tomography systems. I think my favorite was an oil field system. They drilled 2 wells a mile apart, a mile down, and they used one to basically use as the excitation and one for listening for resistance throughout the reservoir, and then use that information to reconstruct a tomography image of the reservoir between the two wells. So there's precedence on similar spaces, and there's precedence on the specific case of eddy current sensing, but it never really took off. So we're going to try and take it and make it much higher resolution than this, and something that's deployable as well within a 3D printing system.
Wow. That's significant. So it's a new materials characterization technique.
Yeah.
Awesome.
Cool. I think, yeah, we went over on time a bit.
All right, yeah, and I just have one more seminar next week. Remember that it'll be 30 minutes earlier. So it'll be on composites for energy efficient buildings by an assistant professor, Kaksha Vinod. So we'll see you guys next week. Thank you.